nanometers. So how the Nanoindenter looks like? This is a part of it, like computers and things will be there. However, this is the Nanoindenter things, and then inside there is a that head. Head looks like somewhat like this, and several different company will having different types, all those. And then at the center there will be a tip here. I hope my cursor is visible. I hope. Then this indenter tip will be various different types of tip is being utilized, and all other different sensors will be there. This is a lateral force measurement. I can use it for the friction measurements and things, and that entire thing sits on a vibration isolation table, because we are talking about nanometer scale depth and things. Then even a small vibrations, low frequency vibrations also, it is a huge, it can be thousands of nanometer, hundreds of nanometers. Vibration itself can change. So we need to use a nano K table, it's called, and then vibration isolation table is there. And then also that you can see there is a entire box, it is a closed box, and after you change everything, your sample, you put it here, and then you need to close. There is a door, say we just close this, and that has all those foam. You can see there is a temperature isolation, so we don't want my instrument is seeing a lot of temperature difference in the room. I don't want more than 1.5 degree change during this measurement. So all those things is been taken care to this measurement, because we as I said, that from millimeter, micrometer, now we are talking about nanometers. I'll be measuring that each nanometers of depth it is going my tip. And so in basically in by angstrom we will be measuring, but nanometer at least we can place it. So it is actually, you can see that I have a maximum load 500 millinewtons with 50 nanonewton resolutions. So I can actually give very small load I can increase. And however, I'll say that in micronewton load range, I'll be having more comfortable of measuring it on that. And depth is here, it is actually micrometers. Sorry for it's a mistake. And with resolutions of very low, means kind of in angstrom range we are talking about. So the in order to control this and take the data out of it, we need to have a lot of control in the atmosphere we are working in. So that's the reason actually this is being in a room where the temperature fluctuation is not more than 1 or 2 degree. Then the vibrations, people are not just coming in, going, and with the doors are hanging, banging. So it is not will not give you good results on that. So that's the we need to have certain control on it. So everything, that whoever that sensitivity, knowing the sensitivity, we need to take care of it. It is even true for human, that people how sensitive people, you have to take care of that. So that way, you need to your instrument also, it needs, you have to give that proper environment to run it, to get it better results. And so I'll give you a little bit of inside of it, even that as I said, that this is the inside that head, and this is just to cover, you are seeing that stainless steel body, because to protect it, and inside is even more sensitive. So this is the shaft, and at the end of the shaft there is a tip attached to it. And so there is a lot of more complication here. It is just a schematic on this, and you can see this is the capacitance sensor attached to this. And as the shaft moves, the distance change, you get the measurement of the depth. And here electromagnetic coil is there to give the force, which is, by varying current in nanoampere, if you can vary, you can get even a nanonewton load variations. So that's the kind of a sensitive things. Entire things is sitting on a spring. You can see there is no other connections as a spring. So you need to know the spring constant very accurately, so that you can incorporate that in your calculations and things. So all those things has been taken care of, that in order to measure in sub nanometer range depth, and nanometer range load. So these are the two basic parameters to be measured, monitored during this test. So that's just to show that how sensitive this instrument it is. So this is a tip we are talking about. So this is actually SCM pictures of those tip, and you can see they are built with various different ways. These are three different types of tip, I'll say. This is a called Berkovich tip, which is a three-sided pyramid. This one face, second face, third face. This is the sharp edge here. This sharp edge means there is a radius associated with that. Anything sharp edge means it is not really the atomic scale edge. We can create atomic scale edge, by the way, for doing some AFM studies, STM studies. We do that by etching process. We can actually create a sharpness which is few atoms in it, that way. So it can be that, even that still it is a round, atom is round. So still it will be, there will be a radius associated with that. These tip earlier, when I started using it in 2000, we used to get tip is 150 nanometers or 200 nanometer in that range. So now I get tip which is 20 nanometers on that. These edge diameters, it's 20 nanometer. And this is also similar three-sided tip, but it is called cube corner. Means the angles of between these are 90-degree normally, and this here angles will be higher, around 120 and all. So these are like depending on how flat they are or kind of very sharp. So those slopes are different. So there are various different types of. This is a conical, means ferroconical it's called, or conical you can say. This is a little sharper, means cone angle is smaller. Here they're a little bit blunt, cone angle will be high. So all these different types of tip used, but most famously used for the nano-indentation mechanical property, like hardness modulus, plasticity index, we use these Berkovich tip. Okay, so next, this more specifically, if I show that this is the, it will be this Berkovich tip, this three-sided pyramid will look like that. When I indent it, it will be like a triangle, and this edge of this kind of a base of this triangle will be all same. Let's say because the tip is like a very uniform, and all sides are same. However, this is being polished, and we are doing it, but still it may not be the perfect one. So that's why a lot of calibration has to be done before we use a tip on that. Even though manufacturer will give a lot of these dimensional aspects, still we need to really do it, run it, and then see whether they are, how perfect they are. And if it is not perfect, we need to fit it in a polynomial and get some data out of it. And this is a kind of a conical tip. As I said, the radius, always it measures that way. If it is a angle is what angle and what is the radius. So it could be starting from like 500 nanometers or even less to it can be several millimeter we use it. But with the nano indenter, we'll be using tip in the range of like a 1-2 micron max. And here I told that this is well, presently we use around 20 nanometers. As I said, that each tip is not perfect. If it is perfect, then area can be, by this formula we can get it. If my tip, this tip is been gone up to HC, my contact depth, if I put a load and push it up to depth of H, then my area I can calculate from this formula. However, this is not very perfect. Always this even the polish I'm talking about in nanometer scale, it may not be perfect. So we don't take any chance. So we do calibrate that. We will be having a known materials, which is we use a SiO2, which is a quartz crystal, single crystal, and then we know their mechanical properties very accurately by other means. And that is a standard sample is available. It is ISO standard samples, and we can measure their properties, and knowing the known property, I can recalibrate my tip area function by we can take various different, instead of only single value, I can take several other values, and then I can put it in a my software to take care of it. Yeah, so let us just go to the next things, and I'll just show few things which is a stress. I talked about stress, and then during this process, two process I showed here. This is the indentation process. There's a scratch process. So in indentation process, what is happening? You have a normal force, and then going down indenter. That means your compressive stress. All are compressive stress at the bottom. Vertically down, and then on the side, what will happen? There will be a tensile stress. Tensile, material will be in tensile, so it can fracture. All those things can happen in these directions. And here also it will be compression. By compression, material can move around and then get a zone. I showed you, then kind of a interactive zone. All those things will happen, and this is kind of a stress distribution. While doing scratch, what is happening? That indenter is moving forward. It's like a plowing. I'm plowing on the soil. It is a, I'm doing the scratch, and then your compressive stress. You see that not only in the forward directions, but also there is a component will be in these directions. In this direction, still tensile stress will be there. So during the scratches also, it will happen. Either it will fracture, then it can pile up. You can see the materials can pile up. This is the surface side, and it has been scratched, and then material will go somewhere. No, so it will pile up on the surface. So all those things during this process, doing this interaction, I am just collecting some informations which is important for me, of that mechanical properties. Basically, I'm just collecting. Sorry. So all those properties will be measuring, by these two techniques on that. Shear hardness, modulus, plasticity index, the here scratch, if I'm doing, then scratch width, depth, how recovery is happening, what kind of fracture is happening, all those things will be measuring. And why we are measuring it? So we need to use these materials. I need to know that whether this will be passing my those conditions where this material has to go on that. So like chip applications I talked about, I give a thin films, after doing that, making that films on the silicon wafer, 16-inch silicon wafer, I give a CVD coatings, and then that coating surface will be very rough and things. I have to do polishing, that's called chemical mechanical polishing. In order to do polish, that material has to be like really hard to withstand even the polishing. So how do I know that? I need to measure these properties and tell that, yeah, this is the properties, it is okay. Now I can polish it, it will withstand. So that's the reason, like always why we do the characterization, what we need to know in that characterization. These are all important aspects. There's an annotation process, like I just showed here how this process will be and what type of data will be. So this is a kind of a, there are a lot of modelings and things are happening, but I'm not showing any of those modeling aspects on that. So the tip, what is happening, the tip, when you start a test, there is a lot of process. You'll be starting a test, and then what will happen, tip will come on the surface slowly, and when it comes to the surface, it has to know that it has come reached to the surface. So there will be a stiffness measurement sensors will be there, and then tip has reached the surface, which the minimum that impact on the surface, it has to know that it has reached. So then only it can assess that very top layers. If I bring a indenter and then bang on it, and then only it has reached the surface, then you try to, by the time it might be poked in maybe several micron, thousand of nanometers, but my whole indentation might be, I'll be doing only 500 nanometers, so I cannot do it. So I need to know when the surface is just touching, it's very barely touching. My fingertip, I'm touching on my palm, so I'll be knowing, even I push it, I'll know I'm pushing it on this, or just touch it barely, I'll feel some sensation. So if I can measure that sensation very accurately, then I don't have to poke my finger on the palm to know that my finger is on the palm. If I just touch, barely touch it, top surface, then also I'll know. So this is the way it works. It is just touching the surface. It will be measuring certain stiffness, and then say that it has been reached. Then it will start giving the load. It will counting the load, And as soon as it counts the load, what will happen? This is the curve I'll be generating, loading curve that is called. So that indentation will happen either load, I am increasing, I am telling that, okay, please indent up to 2 millinewton load, or 1.6 millinewton load. Then it will slowly give certain predetermined loading rate. It will give up to 1.6, and then it will take out that load. Or I can say that go around 500 nanometers, and then you do the indentation. So it will then, what will happen? In order to go to 500 nanometers, it will start increasing the load. As soon as it reaches 500 nanometers, it will stop giving load and do the rest of the process. So the rest of the process, what? We just also at the highest load, we wait for some time, like maybe 10 seconds or 20 seconds, depending on the material. And then you see that there is a small straight line you can see. It means I did not change my load, but displacement of the tip into the surface has gone in. What is that parameters? It is a creep. Mechanical engineering people will be knowing what is creep. So without any load, if my displacement is increasing or my strain is increasing, so that means there is a creep in the materials. So even a simple language, if I say that I have put a wire, a copper wire in tension, and then I saw in between the wire length is around 10 centimeters, and then after 1 minute I see it is 12 centimeter, then it's shed. Copper wires, it became like a, it's no longer a tight rope, because it has been without that tension itself. It actually still strain was happening, and then it is shed. So that's what means we just give that small time, so that those, if it is any kind of a creep, then we just accommodate that, and then we start unloading it. Unloading is happening with the, again, that controlled way. Slowly we'll be taking off the load, and what will happen? You will be generating this curve, unloading curve. These are the three different materials I am just showing here. You can see these three different material, they are unloading, loading versus unloading curves are there. And this is the raw data for me for calculating various different parameters on the surface on this in a. So I did suppose 500 nanometers around the depth, and all these three materials, and these three materials, from seeing these curves, that means to go to this depth 500 nanometers, these materials, the blue, which is a called PET, it is taking load around like maybe 1.1 millinewton. However, BOPET, it is taking almost like 1.5 millinewton load. What it tells to me from this, seeing this itself. So that means the resistance to penetrate of that tip was higher for BOPET samples compared to PET samples. So with a lower load, it has reached 500 nanometers. It takes much higher load to reach 500 nanometer for BOPET. And in between is another samples. So it clearly says that certain, I can say that hardness of this BOPET will be higher compared to this. So this is just a, but how much and things we'll not know. We have to calculate that from that software, and then we know from the model. So that's it. However, yeah, this is the first hand my raw data loading unloading curve it's called, and from there itself I know that a lot of things informations already by this process. I have just collected this data. I know now on this. So what are the things we can do with those data? We can calculate hardness, we can calculate stiffness, and from the stiffness we can calculate modulus of that materials, and then we can calculate plasticity. So plasticity index also we can calculate. So we got hardness, we got stiffness, we got modulus, we got plasticity index. So hardness, we all know that what it is. Modulus, we know on this. So Young's modulus means it is it would be if I take a Hooke's law, I can take a stress versus strain. Stress divided by strain is a my modulus in a linear range. So in the range where you can deform the material, it will come back to that original shape. So that means it is an elastic region. So that's what, if it is a higher modulus, means you will get a higher slope of that curve. And the plasticity index is nothing but how easy to deform plastically. That suppose if I take a materials which is like a butter, which is solid butter in a fridge, and then I take a materials which is a maybe a ceramic tiles. So I can actually take a knife and try to do this. One I can easily poke it easily, just another one I cannot do it, maybe, or very small scratch I can make it. So that means one has a very low pi values, and so it, in order to make a plastic deformations, I need a lot of energy, or a lot of work has to be done to do that in one case, and another case it is very less. So we call it ductile, ductility of a materials. Means if I throw materials from the top on the floor, it will break easily if it is a not ductile. If it is a brittle, you can. And if it is a ductile, it might that absorbs that impact of that on this. So the plasticity index is actually tells that if you have a higher plasticity index, it can absorb more that energy. So all those, I'm measuring it in a tip which is like as a 100 of nanometer area, and then maybe maximum 1 or 2 micron area. I am just assessing. I am measuring these properties, which is like a bulk. Also, we can use it unless this surface is very different than the bulk. I am probing only 500 nanometers. So that means if I as I said earlier, that if my surface is like an oxide layer sitting on this and a micron oxide layer, then I am not measuring actually the bulk properties. I'm measuring the top surface only properties. So I have to clean that surface, bring the virgin surface, and then measure it. So all those things I need to know then on this, because these techniques I am using only the top surface I am measuring on that. So all this property I can measure it. So just some examples of that, how that difference will be. This is a fused silica. Loading, unloading is like this. But copper, if I take, which is, you see that this is much more sharply, it is coming down. So that means, it means that your plasticity index here is much lower, much higher compared to here, because it is takes long energy, very high energy to deform plastically. And that's why it is almost, and if it is completely elastic, this curve will fall on the same loading curve. Loading will, unloading will be same. If it is a perfectly elastic in that region, in this load region, if it is a plastic completely elastic, is this curve will fall here. And this area, you can see area will be more and more if the plastically deformation is happening more and more. So that is and this curve, unloading curve, will be much closer to the loading curve if it is elastic, much away from it, like a copper, away from it, it is a more plastic. So copper, we all know, aluminum, copper, they are malleable, means we can just pull it, or we make it those, that's. So see that property I know, and then what material I can make it is related. So that way you can actually manipulate them, their property for applications. That is all about the material characterizations. So then next I'll go to, what is the time now? 11. Okay. So should we just continue, or we just to take a small
So
break
Arun sir,
so that
no need of break, sir. Continue, sir.
okay,
If you require,
continue. So okay, sure.
if you want required
Okay.
any break, sir.
No, I'm fine. I'm fine.
Okay,
People
sir.
should be fine.
Yes, sir. Yes, sir.
Okay, so far I just talked about that in a single point measurements, like a here, if I have this loading unloading curve, from this unloading curve, I missed to tell that from here I can get a slope which is a stiffness. So at this particular load I can calculate and then make a hardness modulus values on single point. Now I'm just talking about, I want to measure each every point. Like as my tip is going in, I'll be continuously measuring those hardness, modulus, plasticity index, maybe continuously. So in order to do that, instrument manufacturer has done something. During the loading, they put a small vibrational, it's like FTIR type of things. So we just small vibrations of the force we give, so which is actually simulating as a loading, unloading, loading, unloading, loading, unloading, like that, along with the load we are giving. So very small modulation of load we are giving in order to just simulate that loading, unloading kind of a behavior. And from there, I can calculate, means software can calculate that each point it is going in continuously, it will, we can measure that how much is the hardness modulus values. So that's called depth sensing. You know why it is important? So if I have a thin films of 50 nanometers or 100 whatever the thickness, when I am assessing that, I'm trying to do the indentation on top of 50 nanometers. So as soon as I have a 50 nanometer depths, I am reaching actually the substrate. But it will not be so distinct, because as I said that whenever we push it in a load, there is a stress distribution. It can go up to 10 times more than that load, so that area, if I, or 10 times more than the depth I'm doing. Suppose I do 100 nanometers of indentation, my infected zone, or kind of a zone which is affected, it will be maybe, instead of 50, it will be 10 times more, 500 nanometers down. So if I have a thin films which is 50 nanometers, I have to measure the thin films properties. Then I should give, ideally I should give 5 nanometers depth. But 5 nanometer depth, it may not be possible always, because surface roughness might be 10 nanometer, 20 nanometers. So then I cannot do that. So what I have to do? I have to still, I can do that indentation. But if I know that transition, I'll measure continuously hardness for my top surface, it will go, then the interface, then the bottom. If I know that when it is transitioning, then I can calculate from the initial data is for the thin film. In between, it is a kind of a interface, and then the substrate data. So that is the advantage I will be having to know that. Suppose materials is slowly degrading from the surface, I need to know the how much depth it has degraded. Then I need to know that depth sensing indentation. So that is the things we can measure. So just if definitions of that, as I said, the 10% of the coating thickness. So if I have a coating thickness certain values, I did that depth sensing indentation. So my hardness with respect to the depth, my modulus with respect to the depth, but at 10% or 20%, we have to calculate that they are absolute properties. So that's what, for the modulus I take it 10%, for the hardness I can take it maybe 20%. So it is 10 to 20% in that range we need to take, because otherwise you will be taking the data which is influenced by the substrate. So this is possible only I can do test which is depth sensing. So slowly increasing the depth, I am measuring also my properties. So that is the way why we need it. So that is one example. I was talking about the chip making. So this is a, that has interlayer, and then copper, and then there will be in between, there is a low dielectric constant material, so that loss can be less, or insulation will be happen. Those low dielectric constant, as we are going chip smaller and smaller, that low dielectric constant also has to be lower and lower, and lower it, then oppositely their mechanical property goes. So their mechanical property also goes down and down. And while doing any polishing, you cannot do, because they will just, during polishing, they will smear off. So that's what it will happen. So that's why you need to know that their properties. There are such kind of materials. I'm just giving an example. The materials, if I do a indentations, I can see one material is slightly higher hardness. You can see this is I'm doing, and other things you can see this, my hardness or Young's modulus, it is going up and up. Why? Because it is on a substrate which is higher modulus. My that actual material property, I have to take it only this region. After that, it is going up and up. That means my substrate is giving influence. So as I did this test with a depth sensing, slowly depth is increasing, my modulus is increasing, my depth is increasing, my hardness is also increasing, started. So I'll be taking my data, actual that film data is in this region where the plateau region, which is not increasing. So, in this region only I'll be taking for the modulus and hardness on that range. So that is the way we can. So this is actually maybe, how much I have done only 250 nanometers is the depth of indentation. And I'm calculating only 30, 40 in this region, 20. So this means this thickness of this film is actually 200, around 200 nanometers on this. So that is the kind of importance of the measurement techniques you need to know. So this is another examples. This is a coating, substrate which has a different layer, like a coating one, coating two. Now, if I do separately, this substrate and the coating separately, this is the modulus with respect to the depth, my substrate, it is not changing. It is a straight line. That for the coating, it is, and then slowly it is going down because coating is on the substrate. Coating is higher hardness than the substrate. So if I do more and more depth, it will go slowly and then somewhere it will come here as a substrate value. Now, in this entire coating range, I'm doing in indentations. And if I do go slow, you can see it is reaching towards the substrate values. So from one indentation on this multi-layer things, I know this is my top layer in this area, my top layers, coating one, coating two. When it goes down here, it is my one properties. And when it goes down here, I can take my substrate properties. So without doing three different materials together separately, I can do one test and then assess their properties on these. So these, if I know that they are depth, kind of a thickness of those coating. So that's a powerful technique that to assess multi-layers on that. Many times we cannot access the substrate separately. We cannot access the intermediate coating. So we need to do a test and then get that coating properties. So that's a kind of will give you things. Another just a example, another example. During indentation, you can see that coating was a brittle coating. This is substrate, and then coating after indenting, it cut through, and then it was a highly tensile stress. Then it has become like a